So this is going to be a little bit more mundane than money or music. So apologies beforehand. And first of all, I would like to thank the organizers for this privilege. A lot of big people here. And the one thing which really fascinated me was, for the first time, I think we have speakers from 5 continents. This was remarkable. This isn't, I mean, I've been to many conferences in India, but this was amazing. And I think Hilda takes half the credit for that, for getting people from America Latina. Okay, so what I'm going to talk about are experiments which involve pattern fabrication using noise. I work at the physics department. It's a journey of 2 decades and 2 continents. We started in Mexico, and there I worked in this field with my graduate students. And then we were steered towards the application part by people who worked in ciencias aplicadas. And when I came back to India, there was a latency time of about 10 years, and then we retook the experiments and extended and found some new thing, which I'm going to talk about. The final part, the fabrication, was done by this PhD student, Tanushree Roy, and was a part of her doctoral work. Okay, so the assistance comes from a concept called stochastic resonance. It was quite a rage at the turn of the century, but recently it has been on the back burners. And since there are young people in the audience, especially from India, who have been brought up in the universe of collective dynamics, chimeras, and so on and so forth, I thought I'll spend a couple of slides trying to review this concept. In India, there has been very few work done on it. I mean, there might be more, but I'm aware of this logical stochastic resonance by Murli and Sudeshna was done in that. So the concept of stochastic resonance is basically a cooperative phenomena between noise and nonlinearity, which gives you the effect that noise plays a constructive role. Normally, you associate noise with detriment, decrement, and all bad stuff, but this was the first time it was realized perhaps noise, under appropriate conditions, could play a good role. The paper that came first explaining this was by Roberto Benzi et al., although there was another paper, I think by Nicolis, soon after, involving the same concept. And the way it works is there are a couple of necessary conditions, not sufficient, which you need to have this phenomena, which I'll explain in the next slide properly with graphs, cartoons actually, that you need to have a noise which you can tune in the sense that you can change the amplitude and the properties. You need to have an input signal which is sub-threshold, which is not perceptible, doesn't cross the threshold. Nonetheless, when you put noise to it, it does work. So the manifestation is, as pointed out, that due to and because of the presence of moderate or optimum level of noise, you can start detecting signals which perhaps would not be perceptible beforehand. So this is a cartoon we drew to kind of give you a qualitative feeling of what is going on. So in this is a bistable system, so you have nonlinearity. And for the moment, I would ask you to ignore this red dot. So we have simulated the bistability by a W potential, right? And this W potential is oscillating with a certain frequency, which is shown in the top trace over here. So it's just a periodic thing. Now think of the red dot here. And what we are doing is, we're putting a little bit of noise to the motion of this dot. And it is sub-threshold in the sense that due to these perturbations, it is not allowed to cross the barrier to the other way. So it shall remain confined to this barrier itself. Consequently, if I was to draw the time trace of this position of this red dot, it would be fluctuating stochastically within this limit. If I was to start with a different initial condition on the other well, it would keep on oscillating like that over here. Now, if I was to make the red dot perturb with high levels of noise, what the system will do, it will jump stochastically from one well to the other. And it will have a time series which looks like this. So there is no fingerprint of a background oscillation that is taking place in the potential. So it's essentially totally camouflaged, submerged, whatever we want to call it. Nonetheless, something really cool happens when the amplitude of noise is moderate or intermediate. In this case, although the red ball, if you notice carefully, fluctuates stochastically about its local position and goes on from one well to the other, the timing of going from one well to the other is locked with the actual oscillation of the well itself. So if you see there's a one-to-one phase locking between this and this. So it's the kind of a resonance. I think it's a wrong choice of words because noise doesn't have one frequency, but that is what the name was given. So in this case, just to reiterate, for low levels of noise, there's still confinement, there's a subthreshold signal that you can't detect. For high levels of noise, yet again you can't detect the subthreshold signal because there is no fingerprint of the background potential oscillation. Nonetheless, when you have an optimum value of noise, the kind of locking happens in which the ball goes from one well to the other in sync with the oscillation back and forth of the W potential itself. It also manifests itself in vicinity of bifurcation, because bifurcation itself is a threshold. So here you have a system, one of our very early experiments in which you have a fixed point domains in the vicinity of a limit cycle spiking behavior. So when you perturb the system in a sub-threshold manner, you don't cross the bifurcation. So you just have, you just stay there. If you put little level of noise, only once in a while, you cross the bifurcation, and this is manifested by a spike. So at the end of the day, you have a sparsely populated aperiodic spike sequence. In contrast, when you have large levels of noise, you have spurious spiking. So it is spiking even when the subthreshold periodic signal or the square input is not there. Intermediate, again, as we saw in the cartoon before, you have a one-to-one correspondence. Of course, I'm just showing you a section. If you do it for half an hour, you will have some hits and misses as well, right? So it never goes to 100%. And you can quantify the efficiency of your detection by doing the cross correlation between the subthreshold input signal and the spike sequence, which is the output manifestation of the nonlinear system. And what you see is that there exists an optimal value of noise wherein this fidelity to the subthreshold signal is maximum. And I should point out this subthreshold signal need not be periodic. It could be aperiodic as well, and I'll show you some experiments to that effect. So this is basically an overview. After that, there is another phenomena which came out, which was, I think, first studied by Hu Gang, but was made famous by Jürgen Kurz, in which you don't even need a subthreshold signal. All you need is a threshold. So you go from the fixed point dynamics to the spiking behavior. If it's an excitable fixed point, then you get spiking behavior on the other side. And as you increase the noise, for low levels of noise, yet again, irregular spike sequence, which is sparse. High levels of noise, noise-dominated spike sequence. In between, enhanced regularity. I should point out it is not as good as periodic stochastic resonance because it's a purely stochastic effect. Having a determinist component to the subthreshold periodic signal makes it better. But this does exist, and we did study this as well. Okay. We did a lot of work in Mexico before life happened and I had to move to India. But I'm not going to talk about that. This is the external noise. External noise. What I'm trying to convey to you today is essentially what would happen if the noise was internal. With internal, I mean is part of the system. Once it's in the system, you can't extricate it. Because if you have an external signal, you put via an electronic cable a noise, and then you take it off, noise on. In this is part of the signal. And then see the corresponding manifestations of all the resonance effects that I pointed out in the previous two slides. Do they seem to occur here as well? And finally, exploiting one of these techniques, I'm going to give you some results in which we endeavor to make patterns out of noise. Okay, what was the motivation of this? Of course, usually you get motivated when you read a good paper. I had this paper, we read this paper way back, and it said that synaptic noise improved detection. And for us, it was like, okay, they have done it, let's try to see if we can do it in our experimental system. So the goal was, does internal noise or intrinsic noise, I'm going to use these words interchangeably, like its external counterpart, is it able to have resonance phenomena as I have talked about before? And we all know, we don't need to justify that internal noise is omnipresent, right? Okay, so I'm going to talk about two sets of experiments. This is the workhorse for the first set of experiments. It's a electrochemical system which we developed, in which you have the anode, the reference, and the cathode. The electrochemists like to call it the working, the reference, and the counter electrode. So our anode is an iron rod, reference is a saturated calomel electrode, and the cathode is copper. Iron is dissolved in the electrolyte solution of sulfuric acid and a buffer copper sulfate, and the experiments are done potentiostatically. What do I mean by potentiostatically? We keep the potential between the anode and the reference constant, and we measure the current between the anode and the cathode. And when we do a poor man's bifurcation diagram, which is essentially called a voltammogram, in this we sweep the voltage of the system. As I said, my bifurcation parameter is the voltage. Because of that, I keep constant, and I look for different dynamics as I go back and forth. I immediately zoom into a region, identify I have not zoomed in yet, a region in which you see two fixed point behavior sandwiched by oscillations. And this is what we want. We have, as I pointed out before, we want a bifurcation between two different sets of dynamics. So on the left-hand side, we have the Hoff, and when we realized that this looked like spiking behavior, so we kind of zoomed into this, and no longer voltammogram, we actually chose a voltage, let the system evolve for a long time, and look at the characteristics. So in the vicinity, if you look at the voltages I've used here, are in the on the right-hand side of the sandwich window. You see the amplitude of the spiking remains the same. Nonetheless, the time period is increasing exponentially, seems to be, which is kind of indicated of a sniper or definitely a homoclinic bifurcation. We could not identify whether it was sniper or slipper, but it looks like a homoclinic bifurcation. So what we have is a excitable fixed point behavior here and a spiking behavior here. Now, for all the experiments that if not pointed out explicitly, on the contrary, would be placed in the excitable fixed point domain of the system. Okay, so this is the setup. We have already worked with external noise, so that is no longer interesting. So we realized we had the iron electrode. Iron corrodes in acids. We also know the halogens, the chlorines and the fluorines, they attack the surface of iron in a process called a pitting corrosion. And it is also well established in the literature that this corrosion process, which is a pitting corrosion, is a stochastic phenomenon. So what we did the extension, a leap of faith, so as to say, is that can we claim that the concentration or the amount of chloride ions that we add to the system would be the amplitude of noise, internal noise in the system. So we start with that premise that the concentration of chloride ions is the amplitude of internal noise, and then we'll see whether do we get a resonance phenomena as we do the experiment. So just to repeat the protocol, we start the system, we have a certain amount of oil, the chlorine ions, could be KCl in NaCl, and then we do look at the time series, then we clean the entire thing again, polish the electrodes, add an augmented amount of chlorine ion, so on and so forth, sequentially increasing. So this is what the results look like. So in the beginning, did I do something? Did I do something? This is intermittent. So in the beginning, there was nothing, because as I said, I have intentionally chosen the set point to be the excitable fixed point behavior, right? I ain't perturbing, it ain't moving, right? Now, as we increase the noise, which is essentially the concentration of the chloride ions, as I go down, I go to, and this is the corresponding coherence factor plotted for each of these time series. It's very evident there is a unimodal feature to the curve, which essentially implies that the point C of the time series gives you the maximal regularity of the current observed from the system's output. What was really funny and remarkable when the noise is almost zero, you have a fixed point, and also when the noise is very large, is the same fixed point, just more noisy. So it traverses through the entire limit cycle behavior. You realize I'm putting noise, so it's going back also in the other direction. So it's kind of, on an average, you ain't moving the system. So it's not that you're moving in the bifurcation diagram. So this was very nice. So we realize that you do get, this would be the coherence resonance, because I don't have any subthreshold signal put, right? So this was what we did in Mexico, and of course there was and it was funny because he's not a graduate student anymore, he's the head of the department. Marco, when we were doing the experiments, he had a little mirror here to look at how the electrode looked like when the corrosion process was taking place. And then he would say, look, Punit, there is something happening, we should get it checked. So we quickly took the electrode, we took it to the SEM lab, and we did this. And if you zoom into it, and if you're charitable with your observation, you could perhaps say that for the maximum regularity in the time series, the surface appears to be cleaner. Which would, with, and again, a little bit of leap of faith, means that the pitting centers are more ordered. Nothing more, nothing less. So this was done, but it was not of interest for us because we were more interested in looking at the regularity of the current time series that we had seen before, and we did this. But nonetheless, this will come, I'll come back to you because this became very important for, excuse me, later on. As I said, there was a hiatus of about 10 years. At that time, I'd come back home and I started these experiments again, but with a couple of graduate students from the physics department at IIT Bombay. So there was unfinished business. I had done coherence resonance. I wanted to do intrinsic periodic stochastic resonance and intrinsic aperiodic stochastic resonance. So this is the same system that I showed before. The only difference is that you have the subthreshold periodic signal. When there is no noise or there is little noise, nothing happens because you're still in the excitable fixed point behavior. If you have a large amount of noise, the spike sequence is noisy. There is no undercurrent of any subthreshold signal. But at an optimal value of noise, you again see a one-to correspond. This is again a section. If you do it for a longer time, you'll have misses because it doesn't go to all the way. So you have one-to-one correspondence between the subthreshold perturbation or the signal and the response. So if you plot, you could have done cross correlation, but we also wanted to look at the output just to basically repeat the experiments we had done in Mexico to calculate the coherence resonance. So that's this curve, and definitely for the periodic stochastic resonance curve, it shows a very clear maxima at the optimum value of noise. Excuse me. So now, instead of a periodic subthreshold signal, we computationally generate an aperiodic, right, using random number generator. So the system does not know when the next pulse, which is sub-threshold, is going to come. And the question we ask, is the system going to be able to detect whether it's going to happen or not? Well, it's not that good. Nonetheless, there is a value of noise where there's an augmented correlation between the aperiodic subthreshold signal and the spike sequence of the nonlinear response of the nonlinear system. Yet again, to reiterate, no response since low level of noise, nothing is crossing the threshold to the domain where limit cycles are observed, and high levels of noise, no correlation because the spike sequence is stochastically dominated. In between, you do see that, and you have a maximum in the unimodal curve. Okay, so there was this people in the Ciencias Aplicadas, they had a weekly seminario, and I went and gave this talk, and they disregarded everything, and they just looked at the SEM pictures, and they said, we should do that with silicon. And I'm like, why? Because they say, oh, silicon is very important, they make sensors, and if you could have pore distribution which could be regulated, and this and that. And I said, okay. So we said we can do the system. They said no, they want to work in their electrochemical, their idea, their cell. They prefer to work with 2 electrode cells. They prefer to work galvanostatically. So they keep the current between the anode and the cathode constant, and they don't even measure the free potential. They just look at the surface. So the observable is the surface structure, and the control parameter is the current between the anode and the cathode. So again, to reiterate, the anode now we use is P-type silicon because this is what they wanted to see. The electrolyte, it apparently is stronger than iron, so chlorine doesn't do. You have to hit it with fluorine for pitting corrosion. And yet again, our hypothesis, more the fluorine, more the amount of noise, and let's see what happens. So this got done, and we actually then calculated the pore distribution. This is, nanometer scale. This was very cool because it was the first applied paper I have done in my life. And it turns out it does. So what you do is you calculate the average of all these pores, then you subtract your pore, each pore with this average, and you calculate the distribution, and there's a definite minima, for which means that the provoked porous distribution is the most regular. So this was nice. I came to India. It was all lost, but then this guy shook the hornet's nest. So it's funny it's actually nice to read your name, not being criticized. They said that we had done something which could be used. So this was a double-edged sword. They said the work is done, but they say the results shown, can you read this? The results shown that the synthesis of nanostructures can be controlled with noise. This could be applied to control not just the variability in random structures like pores, but also specific properties of more complex designs. So here he was in a backhanded compliment throwing us the gauntlet. You have done the coherence resonance, can you get prefabricated structures using your technique and noise? So this was, again took the same latency period of 10 years. Tanushri walks into the lab and she says, I'll work on it. So just to repeat this, the status that we had when we started this, we get porous structures, we can regulate the porous structures, but there is nothing we can say, this is the pattern I'll give you with noise, right? That would be, something cool. So this will be a spatial manifestation of MSR. Instead of having a signal in time, you have some heterogeneity in space, which will correspond to the fact that in that spatial coordinates, you're closer to the bifurcation, and that would mimic the periodic stochastic resonance in space. So what we did, I'm sorry I said there was no money involved. There is money involved in this talk. So we took this dollar sign, which was, this work we did with BP Singh. He's the optics guy. So he gave us the laser. He gave us this laser pattern. And what we did was we took up this normal, pointer, converged the lens. The pattern passes through the laser pattern. And the rest of the thing, if you've been paying attention, is the same, except instead of P-type, we are using N-type. And the reason being that the N-type is more susceptible to optical etching rather than p-type because of variation in resistance. So we started doing this, and sure enough, this is how I'm increasing the molarity of the hydrofluoric acid. In the beginning, it's just nothing. You don't see nothing that there is, well, there's a brief indication of something is there, right? As you keep on increasing the concentration, this seems to be the best replica of my subthreshold spatial structure. And then, of course, here it's again destroyed because etching has pervaded the spatial domain and more regions are getting pervaded. So then we calculated the spatial correlation between the two, between the threshold, subthreshold dollar sign and the provoked dollar sign on the wafer, on the substrate of silicon. And indeed, you get a unimodal curve where the maxima correspond to what was visually obvious, the replica of the dollar sign. Okay, perfect. So now, unimodal curve. So I just want to point out, here the intensity is milliwatts, right? So 25 milliwatts. So we did, you don't do experiment once, you do it many times, then you show the best too. And then this is with 11 milliwatts. So what would that be? 11 milliwatts means that my intensity of the subthreshold signal is less. So I'm closer to coherence resonance, periodic stochastic resonance. So the maxima amounts of noise that I need to get the best correlation would be higher, and moreover, the fidelity achieved would be lower because this is more stochastically dominated than the previous one. And that is indeed what you see. The black is the one which I showed you before. The red is the one which is with this lower value of the milliwatts of the laser. So this was an example of static patterning. Then Tanushi became ambitious. I have 3 minutes, right? Yeah, the normal question is, why would you do this, right? You just make the laser signal super threshold, get optical lithography, and you're done. And we struggled with that, right? But it turns out, when you do it with the super threshold signal, you can only use the substrate once. In this case, with this low intensity laser impinging on a surface, you just scrub in the beginning, you clean with peroxide substrate, and we use the same wafer again and again, at least 30 times, which is very good because we try to cut corners at cost, because doing experiments in India is not easy. So that was really helpful. And moreover, nowadays this is fashionable, go green, you need to recycle everything. So in this case, the fidelity is not as great as super threshold, but you can use it again and again. You can use different patterns on the same substrate. So it's a little adaptive. So this is the dynamics patterning. Then Tanushi became a little adventurous, which was very, contrary to her personality. So in this, you'll see this dot, laser dot, traversing to the right. So this is the dynamic patterning. This is real time. So we are moving with a step motor. So the laser signal is going to the right. And the same setup, the mesh and the silicon, we are still with the same, since everything is the same. So in this case, what should be the output fidelity with? To a straight line, yeah, because this is what you are traversing through the subthreshold signal. And indeed, so you go from the lowest velocity to the highest. If you go very high, nothing happens. The system does not have the time to react. If you go very low, you have etching everywhere on the surface of the substrate. Nonetheless, I reckon, I don't know, you think G is the best fidelity to the signal. So these are the different velocities going from low to high, and then you see, we did it for, you have to point out, in the entire set of experiments, the amount of noise, I'm sorry, just 2 seconds, amount of noise is kept constant, okay? So we just changing the velocity. We did it with different concentrations, keeping the same value, and just as the last figure, all 3 experiments that we show here have a very clear unimodal feature, wherein the maxima implies the level of velocity for which you get maximum fidelity to the straight line. With that, I thank you so much for your patience, and I'll try to answer questions to the best of my ability. Thank you so much.
Thank you, Professor Paramananda.